Good morning. We've now finished the first part of the course. In the first part of the course, we looked at all of the theory involved in derivatives. We understand where they came from. We understand how to interpret them. We understand how they relate to continuous functions. And finally, we understand what the second derivative is. In the second part of the course, we're going to start developing a whole bunch of derivative shortcuts. Because right now, pretty much the only way to compute a derivative is to use that limit definition. So a couple of things about this. First, I'm well aware that computers, calculators can compute derivatives for us. That's true. So what's the point of this part of the course? From my perspective, this part of the course is for us to really understand where all these formulas came from. So that's one of the things about a math class versus maybe an applied math class or a science class, where the real focus is on applying or using the formulas. Here we want to understand what they are so they're not some sort of black box. So today we're going to learn how to find the derivative of something that looks like this. So you can compute the derivative, but it would be a pain. I mean, you'd have to do the limit definition, and you'd have a quartic in there. You'd have x to a power. Not fun. So this is what I'm going to do. I'm going to abstract this problem and think about what is actually going into that function and come up with shortcuts for the abstraction and then apply it to this function. So what do I mean by that? Well, if I look at this, I really have a sum of things. So let me try to come up with a derivative of a sum in general. And let me just be clear about this. This is a specific f of x. Now I'm talking about, hey, if you have any f of x and any g of x, what's that derivative? Now let's look at each of the pieces. Well, this guy is really just c times x to a power. And I know how to do the power rule. This is c times x to a power. This is c times x to a power, where x to the power is x to the 0. So I'm also going to spend a little bit of time coming up with a formula for that guy. Finally, we already know that the derivative of x to the n is n x to the n minus 1. So a note about this notation, this d dx notation. So we've seen dy dx. If your y happens to be something more complicated, like f of x plus g of x, instead of sticking it up here, we put it down here. It's just a lot cleaner. So this d dx is still saying, let's take the derivative. So once we know how to take the derivative of the sum, constant, we already know this, then we can answer that problem. Now, yeah, this is a bunch of work, and maybe it would have been quicker to just do the limit definition, but once we do this once, we can actually use this with any polynomial. So it'll pay off. So let's check this first guy out. We want the derivative of f of x plus g of x. Well, what I'm going to do is I'm going to write out the limit definition for this guy. So let's see, our function is f of x plus g of x. I'm going to plug in x plus h wherever I see an x. And I'm going to divide that by h. So I need to evaluate this limit. Now, we're actually developing a proof here. We're trying to prove what this formula is. And one technique that could be helpful with proofs is to ask yourself, well, what the heck do you think the answer is? Now, thinking back to limit properties, and limit properties are now going to start popping up all over the place, we saw that the limit of a sum was the sum of the limits. Well, the derivative is a type of limit, so it wouldn't surprise me if the derivative of a sum is the sum of the derivatives. Now, I might be wrong, but it wouldn't surprise me if that were the case. So that's what I'm going to hunt down first. And if you look up here, we've got an f of x plus h minus f of x lurking about, and we've got a g of x plus h minus g of x lurking about. So this is looking pretty promising, because those are both part of the definition of the derivative for each of those guys, f prime of x and g prime of x. In fact, let me see if I can reorganize this so that we can see that explicitly. So I'm just reorganizing the top, f of x plus h minus f of x, plus g of x plus h minus g of x, and that's all over h. But if you have this, 1 plus 2 over 3, you can write it as 1 over 3 plus 2 over 3. And in fact, I'm going to do that right now, because then I can very clearly see that I've got my pieces for the derivative of f of x and g of x. So at this point, I know the limit of a sum is the sum of the limits. That was one of the properties. So I can break these guys into two pieces. And then what do I have? I've got f prime of x, and I've got g prime of x. Beautiful. The derivative of a sum is the sum of the two derivatives. Again, going back and forth between both prime and ddx notation, you want to feel comfortable with both. Okay, so what does this mean? This means that to compute this derivative, I can compute each piece term by term and then add them together instead of doing it all in one fell swoop. Awesome. So now, if I can deal with that second piece, I'll be able to compute derivatives of any polynomials. So let's take a look at the derivative of c times f of x. Well, I'm going to give you a minute. Pause the video, please, and see if you can write out the definition of the derivative for this function c times f of x. Well, hopefully we said c times f of x plus h minus c times f of x all over h. Well, what can we do algebraically here? Hopefully you said you can pull that c out. So we have the limit as h goes to 0. C times f of x plus h minus f of x all over h. So one bit of algebra here. I feel like this is asked every quarter, so let me actually point something out. So if let me do that in actually 2 steps. Let me do it. Okay, so technically, here was step 1. So I pulled it out on the top, and then I pulled it all the way out over here. Now, hopefully you believe that, because if I have 3 times 5 over, 6, isn't that the same thing as 3 over 1 times 5 over 6? It's like I'm doing multiplication backwards. And then 3 over 1 is just 3. So that's where this is coming from. And I'm gonna be doing that a bunch of times. So let's make sure we understand that point. Pause the video if you need to. Okay, let's get rid of this. All right, going back to my limit properties, the limit of a constant times a function, we're allowed to pull out that constant. This was one of our limit properties. So I just pulled out the c. And what is this? This is the derivative of f of x. Beautiful. This means that constants can just go along for the ride. They're unaffected by this process if you're multiplying them. You can just pull them right on out, not worry about them till the end. Okay, so here are all the pieces. I invite you to pause the video and see if you can come up with this derivative now. Again, don't do a limit definition. Try to use the results that we just came up with. All right, hopefully you paused the video This tells us that we can just look at them term by term. Okay, so the derivative of x to the fourth is 4x cubed. The constant just goes along for the ride, so it becomes 5 times 4x cubed. The derivative of 2x, well, one way I can think about that is that's just a linear function. And the derivative of 2x, since the slope is 2, is just 2. The derivative of minus 1 is 0, since that's a constant. And again, I can add these guys, and I am done. A lot of work getting there, but now it's easy for us to compute derivatives of any polynomial. Give this one a shot. Pause the video. Okay, so again, the 3 comes down. And this just goes along for the ride. The derivative of 18x is 18, and I'm done. Now let me point something out in terms of how I think about these. If you notice, this 5 became 4 times 5. This 6 became 6 times 3. So from now on, I want you guys to get used to the following. Just take this, multiply it by this, boom, and then n minus 1. So for example, f of x equals 11x cubed. So I automatically just multiply them together, because that's what's happening, and then subtract 1 from the exponent. All right, as in an application example, let's tie together increasing, decreasing, concave up, concave down, and polynomials. So example, let's say, where is f of x equals x to the fourth minus 4x cubed, decreasing and concave up. So I want this guy to be both decreasing and concave up. So what am I looking for then? If this guy's decreasing, I want f prime of x to be less than 0. If this guy's concave up, then I guess I want f double prime of x to be bigger than 0. I think a good technique in problem solving is before you dive into all the details, you need to articulate to yourself, what am I trying to solve here? What am I trying to do? And I'm really looking for this stuff. So this will involve sign charts, finding out where the first derivative and second derivative are 0, positive, negative, etc. So let's check it out. F prime of x is, well, pause the video for a second. Hopefully you said, oh, that's 4x cubed minus 12x squared. I'm going to do some work with the sign chart. Let me save some space there. F double prime of x, pause the video, give it a shot. So hopefully you said that that's 12x squared, bring the 3 down, minus 24x. Okay, we need to find out where this guy is 0 and not define, and then create the sign chart. This is always defined because it's a polynomial, so let me set it equal to 0. At this point, you want to factor. So we have 4x squared, pulling that out, and it looks like I'm left with an x there and a minus 3 there. So it looks like on my sign chart, and I would highly, highly recommend labeling your sign charts f prime, f double prime, or it can get very confusing. See, x is 0, x is 3. Those are the two zeros. And then I'm going to use this guy to figure out where my first derivative is positive or negative. I'm going to use this guy instead of this guy because this is product and this is a difference. And with products, it's way easier for me to see if the whole product's positive or negative. I just need to look at the smaller pieces. So in other words, if I plug in a number bigger than 3, like a gazillion, this is going to be positive, that's going to be positive, and the net result is positive. I plug in a number between 0 and 3, like 1, I get positive, positive, negative. That product is negative. If I plug in negative 10, I get positive, positive, negative, or negative. So this tells me that f of x is going to be decreasing, decreasing, increasing. All right, so f prime of x has to be less than 0, so this isn't even going to work for me anywhere here. So I'm just going to get rid of this stuff. Okay, so let's look at the second derivative. Let's see, f double prime of x equals 0. We want to see where that's true. So I'll give you a minute. See if you can figure out where this guy is 0. Right, hopefully you pause the video. This is always defined, by the way, so I don't need to worry about that. It's going to be 0. Well, let's see, I can factor out the 12x. And this guy's going to be 0 when x is 0 or x is 2. Okay, so let's put this on the sign chart. The sign chart is the f double prime of x sign chart. Again, you want to keep your head above water with that. Make sure you know what your sign chart's about because that's going to tell you where you're plugging things into. So here we're going to plug them into our second derivative. If I plug in my favorite number bigger than 2, which is a million, billion, gazillion, that's positive. That's positive. That product is positive. Favorite number between 0 and 2 is 1. That's positive. That's negative. So that's negative. Favorite number less than 0, how about negative 10? That's negative. That's negative. That's positive. So we want to find the places where f double prime is bigger than 0. So that'll be here and here. So I don't even need that. So I'm going to give you a minute, see if you can find where this guy is both decreasing and concave up. And again, this to me is amazing. We're doing this without even graphing it. We're doing it just by studying the derivatives. So pause the video and give that a shot. Right, well, hopefully you said f prime of x is less than 0 and f double prime is bigger than 0. Well, that's going to be true, looks like, let me articulate concave up, concave up. That's going to be true if x is less than 0. So I could write it from negative infinity to 0. And there's actually another place, which is a little bit hidden. So f prime is negative between 0 and 3. F double prime is positive from 2 to infinity. So if I go from 2 to 3, both of those conditions are true. Right? From 2 to 3, this guy's negative. From 2 to 3, this guy's positive. So it'll be from negative infinity to 0, union from 2 to 3. And just a subtle point, but kind of important, this is the union symbol. In English, we could write or. We wouldn't actually write this interval and this interval. Because what that's saying is, yeah, this will be decreasing and concave up if x is both here and at the same time here. And there are no x's that are both less than 0 and between 2 and 3. So that's why you should use the union symbol or. All right, so today we learned how to deal with derivatives of sums of functions, and we learned how to deal with derivatives involving constants times functions. And this not only enables us to take derivatives of polynomials, but we can actually take derivatives of sums of any types of functions as long as we know the derivatives of the individual pieces. So in a future section, for example, we could take the derivative of e to the x plus 2x. That's just one example. All right, that's all I have to say for today. Thanks for listening, and I will see you next time.